How does a computer stop one tiny broken wire from crashing the entire internet? And how does it read and write data at lightning speed? Today, we open the Master Builder's Playbook to learn how servers stay alive using resiliency patterns. In our physical world, things break. Pipes burst, wires cross, and traffic jams up. The digital world is exactly the same. Even the biggest websites rely on physical computers that can easily get overwhelmed with too much traffic or faulty connections. The people who design these systems, our master builders, know that failures are guaranteed. So instead of hoping things stay online, they build specialized tools into the code that are designed to handle the breaks safely. Building a reliable system means accepting that accidents will happen. The goal is making sure the network survives even when one small piece eventually gives out. Think about a sudden power surge in your home. Instead of letting the extra electricity rush in and start a fire, a tiny glass fuse in your electrical panel intentionally blows itself up to stop the spark's progress. We face a similar problem with computers. Imagine one computer, we'll call it Service A, needs info from a second computer called Service B. If Service B is broken, Service A will just keep knocking, wasting energy as it waits for a connection that will never happen. If enough computers get stuck waiting like this, the traffic piles up. Soon, the entire system grinds to a halt. One tiny local failure spreads until it brings down the whole network. To stop that spread, master builders use a digital version of that house fuse. This tool is what they call the circuit breaker pattern. This map shows how a digital circuit breaker works. Think of it like a drawbridge over a river. When everything is working perfectly, follow that unbroken green line on the left. We call this the closed state. The drawbridge is down, and the messages are flowing back and forth without any trouble. But if the system hits its limit, say 5 failed messages in a row, the circuit trips. Look at that red jagged line in the middle. It shows the system has reached its breaking point. Now the drawbridge goes up. This is the open state. Instead of letting traffic pile up, the system turns new messages away immediately to save the rest of the network from overloading. After a little while, the system tries to recover. It enters the half-open state, where it sends out a single cautious test message, that dotted line you see on the right. It is like letting a single car drive out to see if the bridge is safe. If that one car makes it across, the system knows it can safely drop the drawbridge for everyone else. By cycling through these 3 steps, a broken bridge stays isolated, the failure is contained, and the rest of the digital city stays moving. Computers face another challenge: trying to do too many different things at once. To see the problem, imagine walking into a busy restaurant kitchen. If a single person tried to cook every meal while reading the menu to every customer, they would eventually collapse under the pressure. The solution is to separate the roles. One chef only cooks the food, while a waiter only reads the menu to the customers. We do the exact same thing when we design systems. We take the job of reading information and the job of changing that information and pull them apart into 2 distinct nodes. This is what engineers call Command Query Responsibility Segregation, or CQRS. The heavy tasks that actually change the information, like adding a new user or deleting a file, are the commands. These go to our chef, a database built just for those heavy changes. Meanwhile, the tasks that just look up information are called queries. These go to our waiter, a lightning-fast database that only focuses on reading and showing you what you asked for. By splitting the work this way, the system stays fast and responsive, no matter how many people are using it at once. The circuit breaker pattern gives our network a vital fuse. It ensures that when one part of the digital world breaks, it doesn't take the rest of the world down with it. And the CQRS pattern keeps everything organized. By separating the work of reading from the work of writing, computers can handle massive amounts of traffic without breaking a sweat. These patterns ensure that the websites and apps we use every day stay fast and reliable, even when the underlying hardware is facing a crisis. Next time, we will learn how a single digital front door, an API gateway, safely hides a massive network of secrets when we explore those specialized helper programs we call sidecar architectures. Thank you for watching.